Hello, algorithmicians. We're just going to have a little cheeseburger-sized nugget bit of maths, which is going to help us with, well, it actually helps with 2017 question 14, which is to do with dividing limits for time complexities. The maths for this is quite nice. I don't know how likely it is to come up again, but it doesn't hurt. So, quick reminder of the dominance of types of functions. We know that combinatorics, like factorial, grows the fastest, followed by exponentials, and then polynomials, and then logs. And there are some other ones that we could throw in there as well. But this dominance is important. I've also listed some combination rules here. We're just going to really be focusing on the quotient rule, and the other one you've probably kind of used is the sum and the product. So let's see how this works. We're going to find the limit of this sequence where we are dividing one thing by another. So we might be tempted to expand this, so we actually don't need to, but we will, 2n squared plus 5n plus 2 over 3n squared plus 3n. And we are going to consider the limit of this, so we'll call this f of n. We're going to consider the limit of f of n as n approaches infinity. And the way we're going to do that is divide everything in the fraction by the most dominant term. So looking at the terms we've got, 2n squared, 5n, 2, 3n squared, 3n, we are going to divide by n squared. That is the most dominant term, which gives us 2 plus 5 over n plus 2 over n squared over 3 plus 3 over n. And at this point, we can say, well, the limits of, so this bit, and this bit, I think we can see quite easily, as n gets larger and larger, those bits all approach 0. So the limit we end up with is just 2/3. Now, if this was somehow a time complexity, I mean, it doesn't make sense as a time complexity, but if it was, we would therefore say that this function is in constant time. Okay, we're just going to go through and do a few of these and then see how it can be applied to that cheeky question which caught a few people out. So this one, we've got to decide what is the most dominant term. It's the factorial, so that gives us 2n squared over n factorial plus 10 to the power of n over n factorial over 1 plus 3n cubed over n factorial. We'll call this f of n, and now the limit as n approaches infinity of that thing. Well, the first bit, we know that because n factorial gets larger than 2n squared, like more quickly, this approaches 0. Same argument for the 10 to the n over n factorial, that approaches 0, 1, and then same argument for the bottom right, we have 0, so the limit of this is going to be 0, which would make no sense at all for a time complexity, but hey, that's just where I took these examples from. Try the next one, and you may think, oh, it's obvious, but anyway, it's also fun, so give it a go. Should be pausing this as we go. So we have 1 plus 2 over n plus 3 over n cubed over 2 plus 1 over n cubed. So then the limit as n approaches infinity of that thing is going to be just a half. So once again, we'd have this thing in constant time. Moving down, this one is a little bit saucier. So we're going to be dividing by 3 to the power of n here. So n squared over 3 to the n plus 2 to the n over 3 to the n over 1 plus n cubed over 3 to the n. Then the limit as n approaches infinity of this thing. So the first one here becomes 0. This one, because they're both to the power of n, we can actually rewrite this as 2/3 to the power of n over 1 plus 0. So this is going to be 2/3 to the power of n. Now, this could be a time complexity, except that 2/3 is less than 1, right? So, and it wouldn't make sense to talk of limits in that case. But what we can say here, as n approaches infinity, 2/3, we know from our work on hopefully geometric sequences, this would approach 0. Okay, the maths there is quite cool. If it was different numbers, we'd have a different time complexity, but it wouldn't make sense to talk about it as limits. Okay, and the last one before we look at the exam question, dividing by n factorial again. So we would have, I should have put those in first, shouldn't I? Oh well, whatever. Equals 1 plus -1 to the n over n factorial over 2 to the n over n factorial plus 3. Now the negative here might throw you, but it actually doesn't affect where this goes. Like this still approaches 0. Like it, might sort of oscillate between positives and negatives, but we end up with 1 plus 0 over 0 plus 3. So as n increases, this would be doing something like this, approaching 0 from both directions, which would give you a third. So again, constant time. This one is more interesting, although also I don't think it makes a lot of sense. So in one sense, I'll show you what I mean. We've got two functions, this one where you add them together, this one where you divide them. So we know that when we add functions for big O notation, we choose the worst term, and that becomes our time complexity. So we've got 4n squared plus 6 plus 4n squared plus log n. The worst thing is n squared, so this has time complexity, big O n squared. So we're looking at B or D. Now this next one, I think when people look at this and say for f of n over g of n, we want to say it's 4n squared plus 6 over 4n squared plus log n. I think a lot of people would want to call it this one here because you sort of see the maths in big O notation is dodgy sometimes, but it's not so dodgy that we can just forget how fractions work. So we are going to divide everything by n squared. We have 4 plus 6 over n squared over 4 plus log n over n squared. These two functions, because the bottom term dominates, they disappear. We are left with 1. And so we have d big O of n squared for the first one, big O constant time for the second one.